Okay, so in this lecture, we're going to look at the idea of electromagnetic induction. And electromagnetic induction is a pretty hard concept to understand, so we're just going to introduce this idea. And when you come back to class, we're definitely going to talk about it a lot more. Again, if you've got questions, just write them in the margins of your notes or post them in the discussion section. So to kind of start off with electromagnetic induction, we've previously seen that a moving electric field, so a moving electric field is just a current, right? So a moving electric field, which is just AKA a current, creates a magnetic field. And we've looked at what that magnetic field looks like in terms of right-hand rule number 1, etc. And a guy by the name of Faraday, and so this is just one of those kind of, yes, it's important to know who did this. A guy by the name of Faraday discovered that a moving magnetic field can create an electric field. So Faraday discovered that a moving magnetic field can create an electric field. And that electric field can cause charges to move. And so this is a really important discovery in the fact that all you have to do to get a charge to move is to have a changing magnetic field. And so it's really kind of revolutionized all the applications we've done. So it's a pretty important idea. So all that's needed is relative motion between a magnetic field and a wire. So all that is needed to generate a current is relative motion between a magnetic field and a current. So you can either have the wire moving near a magnetic field, or you can have the magnetic field moving near a wire. And we're going to look at cases of both. Okay? So with this, again, this is how you create a movement for a charge. This movement for a charge is a fancy term called induced EMF. So induced EMF is just essentially the induced voltage in a wire that causes the charges to move. And it's actually a terrible name. EMF stands for electromotive force, because it was first thought, like when they first looked at this idea that if I have a magnetic field and I have a wire and it's moving nearby and all of a sudden the electrons in that wire start moving, initially it was thought that, oh, there must be some force that is causing those charges to move. So they called it the electromotive force, the electron moving force. And then later on they realized, well, it's not really a force, it's just this idea of induction, of a changing magnetic field, changing electric field that's causing the charges to move. And so they attribute it to more of a voltage difference, because we looked at in the previous chapter with circuits that a voltage difference is what causes charges to move. So when they realized it was actually just a voltage difference, they didn't go back and change the name. They kept it as electromotive force, they just acronymed it, so it's EMF. But EMF, induced EMF, is just a voltage. It's not really a force, all it is a voltage. But it's a very specific type of voltage. It's not a voltage that we're going to create using like a battery. So a battery uses chemical potential energy to have a difference in voltage between the anode and the cathode. This is not that kind of voltage. This is a voltage that we're creating just because we have relative motion between a wire and a magnetic field. So because it's a very specific type of voltage, we're going to give it a specific symbol, and the symbol is the Greek letter epsilon, standing for induced EMF. The units, though, are still going to be volts, because this is still just a voltage value, okay? And we will look at an equation a little bit later, but because we just want to really understand conceptually what's happening here. So if we look at this idea of induced EMF and kind of think about, well, what depends, or what determines how much voltage I have? What determines how many charges are going to actually get to move when I have this relative motion? It depends on the amount of change the magnetic field goes through. Let's say this. So it's the amount of change in the magnetic flux in a given region. The amount of change in the magnetic flux in a given region. Because again, all it is how is that magnetic field changing near this wire? So if we think about, well, how can the magnetic flux change? How can the amount of magnetic field lines I have in a given region change? There's a couple of factors that it depends on. One of them, it's a pretty obvious one, so let's actually say this change can occur due to a change in magnetic field strength. So if my magnetic field is increasing or decreasing near my wire, that can cause an induced EMF. A change in the orientation of the wire. So again, just relative motion. So let's say I have an existing magnetic field, and let's just draw it out. Let's say I have an existing magnetic field, and I have a wire that's running through it, and my wire looks like this. If all of a sudden I move my wire to be like this, I will have an induced voltage in that, and I'll get some current to actually flow through the wire. Right? Just by changing that orientation will cause an induced EMF. And the other thing that can cause this change is the amount of wire that is exposed to the magnetic field. So again, if I change that amount of wire that's being exposed to the magnetic field, I can induce a voltage. And primarily, we see these effects with loops of wire. If we have a single wire, we see a little bit of the effects, but it's more noticeable when we have a loop of wire. So we mainly see the effects of induced EMF when working with loops of wire or working with solenoids. Because just like how we saw previously, when I have a straight wire, I definitely have a magnetic field around it, but when I loop the wire, then that magnetic field grows stronger inside the wire. The same thing is going to happen. If I have a concentration of magnetic field lines inside my wire, and all of a sudden something changes, I'm more likely to affect the charges or the electrons in that wire and cause them to move to create a current. So I know that this is really abstract, and we are going to hit this again when you come back into class and go over a lot more to really understand the nitty-gritty of like what is happening step by step when I'm changing my magnetic field, like what is innately happening to the electrons in that wire, and why is it that I'm generating a current. But hopefully this kind of just gives you a little bit of a primer, and then when we come back to class, we'll go at it again, and it'll be a little bit more concrete the next time we talk about it, okay?